Hello, and welcome to Chapter 3. Relational Databases. Relational database is the most common type of database today, and is de facto standard used in almost every industry, from various web services, industry applications to robust transaction systems used in banks. The concept of work is based on the relational data model designed by Edgar Frank Codd in the 1970s. For a relational database, we say it is a structured group of data or records that are stored within relations. These relations are essentially mathematical concepts and they are represented as logical objects, commonly known as tables. Relationships between different tables are realized using primary and foreign keys, which enables data to be linked between different objects. It also includes a group of other objects such as views, stored procedures, functions, users, transaction logs and other database objects, but this greatly depends on the database management system in use. The data itself is organized in tables with rows and columns. Each table represents an entity, and a row in the table, which is called stored record, represents a separate occurrence of that entity or an object about which we store data, for example employee. Named columns indicate the attributes of that entity, for example job title with value design engineer. The set of values that a specific attribute can take is called a domain, where all data in table must be within defined values and of the same predefined data type. For database management, we use RDBMS or Relational Database Management System, which is a type of software that enables storage, organization, and processing of data, ensuring efficient and reliable management of databases in the relational model. Today it is a key tool in the world of information technology because it enables reliable and consistent data management in various applications and industry sectors. It sits between the physical structure of the data and the user who accesses it. Essentially, it stores and organizes data while also ensuring data consistency and integrity. In short, database consistency means that the data in a database is the same across the system and throughout its lifecycle. This means that all users of the database will see the same data, regardless of which system they use when they are accessing the data. Integrity means that the data in a database is accurate, complete, and reliable. RDBMS also allows users to perform various operations on data, using SQL or structured query language. Users and administrators can use it to administrate database, or to create, retrieve and manage data, and to perform various analytical and statistical operations on it, about which we'll talk more in the next chapters. Next important concept in database theory is referential integrity. By referential integrity we mean the process or procedure of preserving the consistency of data among related tables or relations. We do this by defining a parent-child relationship between the tables. Once the relationship is defined, the referential integrity will not allow us to enter data into the field of the child table if the same value does not already exist in the parent table, that is, table to which we refer. A similar thing happens with the deletion of related data, where the deletion is disabled if we have not previously deleted it in the child table. To accomplish this, we use various constraints which are applied either at the level of an individual column, or at the level of table. For example, the parent table contains and provides its primary key information to the child table, where this same value can be found as a foreign key value. Together, primary key in the parent table and foreign key in the child table form a relationship between those two tables. Since relational databases are based on relations, and connecting data, the ability to identify each individual piece of data is of crucial importance. Such identification makes it possible to find a record whose search is based on a record from another table, whereby we create a connection or relation between parent and child tables. Primary and foreign keys helps us in this. Primary key indicates a unique value assigned to an entity, to uniquely identify each individual occurrence of that entity within a table. Since we use it to uniquely determine each record, it includes one or a combination of several columns that are grouped into one key, in whose row we cannot have a value that has already been assigned to another row. Each table can contain only one primary key. Also, the integrity rules dictate that the value of the primary key must not remain unentered, that is, value null. The primary key is usually denoted by the abbreviation PK. Foreign key is an object that in combination with the primary key from the parent table forms a connection or a relationship with the child table. When we add foreign key to a table, we create a connection between the table on which we created it, that is the child table, and the table to which the foreign key refers to, that is the parent table. Once the relationship is created, each occurrence of entity before being entered into the child table must have its corresponding record in the parent table. The exception to this rule is that we set the foreign key in the child table to be null. This allows us to somehow bypass the entry under that attribute which would otherwise be mandatory. The foreign key is usually denoted by the abbreviation FK. Basically, each table in a relational database has one or more keys. The primary key uniquely identifies each row in the table and ensures data uniqueness. Foreign key allows tables to be linked to other tables and to create relationships between them. As we already said, integrity of data is very important, and to preserve referential integrity of data, we use constraints. Constraints are objects within the RDBMS system intended to preserve the integrity, consistency and quality of data. These are restrictions that we divide into several groups, so we have restrictions based on keys, for example, primary key, and restrictions based on the domain, for example check, and not null restrictions. Domain-based restrictions ensure that the data values of a particular column or set of columns meet certain criteria. Thus, for example, for information containing grades of a student's exams, it is possible to define a check constraint that will allow the entry of values only from 1 to 5. This eliminates the possibility of entering incorrect data, example grade 6. The restriction is active when entering new as well as when updating the existing data. Key-based constraints are based on each row. The best example of such a restriction is unique, which prohibits 2 rows within the column to have the same value. So, for example, if we create unique constraint on the field personal identification number, the constraint will not allow creation or update of that specific number as the number already exists. The default restriction defines what will be written in the new record if the value has not been explicitly entered. So if we entering new data for a certain entity, and for some reason we do not enter a value for certain attribute, it will take on the default value that we define for it. It can be defined as a certain numerical value, for example 0 or 100, as a text record unknown, yes or no, or as one of the system functions, for example getDate, in which case current system's date and time will be automatically filled in that place. The default constraint only works when entering new data, and not when updating existing or deleting it. We have already seen that relational databases allow tables to be connected through relationships which are established using primary and foreign keys. This makes it possible to efficiently query data and perform complex queries that cross the boundaries of individual tables. This way we don't have to store all the data in a single large table but spread them into multiple smaller ones, which in the end saves space, improves performances and speeds up query execution. So, according to the number of maximum possible entity occurrences we have in parent and child tables, possible relations between the tables are 1-to-1, 1-to-1 or many, 0 or 1-to-1, 1-to-0, 1 or many and many-to-many. So for example, if we have single occurrence for entity and employees, and single occurrence in the table employee details, it means we are forming 1-to-1 relationship. This means that the column employee ID, which uniquely identifies employee, is the column in both tables. It is the primary key in the table employees, and a primary and foreign key at the same time in the table employee details. What this means in the end is that each employee in the table employees can have only one details record in the employee details table. At the same time, each detail record in table employee details can be connected to only one employee. In case of 1-to-1 or many relationship, we could for example have one record in table university, for example Princeton University, and one or many records in students' tables, and so on. Another important thing in database design is normalization. Normalization is a process or technique of designing a relational database that aims to break large relations into smaller groups of data, which saves space and improves performances. It actually speeds up the execution of queries and retrieving of data. Perhaps even more important goal of normalization is to reduce or even eliminate redundancy or duplication of data. It also ensures its consistency and completeness. This is because it is very difficult or almost impossible to maintain data integrity in a database that stores the same information in several different places. If we were to store information about several entities in the same or multiple tables, and if we would not make data changes in all the places where data occurs, we would bring the database to an inconsistent state, and thus enable possibility of providing contradictory information. This could lead to inconsistencies and anomalies. The same thing happens when deleting or entering new data. In order to bring the table to a normal state, we use the so-called normal forms. A series of rules that we must apply in order to bring the database to a certain level of normalization. So, here is the table of normalization rules. On the left side we have degree of normalization, and on the right are the rules we need to apply to bring the table to a certain level or degree of normalization. First rule says that an entity is in the first normal form state, or 1NF, when it does not contain repeating groups of data, and when its attributes are indivisible or atomic. For example, when the table does not have multiple values in attributes that can be further broken down. Second normal form says that an entity is in 2NF when it satisfies the rules of 1NF, and when all its attributes are fully dependent on the entire primary key of that entity. And for an entity to be in third normal form, or 3NF, it must satisfy the rules of first and second normal forms, and all its attributes must depend only on the primary key. Also, the entity must not contain derived attributes. Here is an example of how non-normalized table might look like, and how we could bring it to 1NF. We see that table is a mixture of student names and subjects they are attending, and also contains multiple values in some attributes, so column subject contains multiple values like mathematics, physics, and so on. If we apply first normal form rule, and split values or attribute from column subject so that each attribute contains only atomic values, that is, that attribute cannot be split further, we would bring table in 1NF, or first normal form. Here we see that every subject is in its own row and each attribute contains only atomic values. This means that table is in 1NF. To continue with 2NF, we have to split the original table into two, student and subject. The student table should contain information only about students, and the subject table should contain information only about the courses students are attaining. This step will allow each attribute in the table to refer to the entire primary key. Here is the table student. And here is the table subject. Finally, tables student and subject do not contain derived attributes, so they are already in 3NF, or third normal form. For another more proper 3NF example, let's take an order details table where we have a derived attribute in column total. Its value we can easily get by multiplying columns quantity and price. The rule of 3NF says that we should not have derived attributes. If we remove it, we would bring the table to 3NF, or third normal form. So here is the order details table in 3NF. Sometimes, from a normalization point of view, a table column needs to be intentionally derived from other attributes for performance reasons. Simply put, a query which lists everything where attribute total is greater than 250, that is where the total price is manually calculated and stored in field, is performed much faster than a query where the system recalculates value every time for each record. For example, list all where price multiplied by quantity is greater than 250. Such a derived attribute can then be indexed, so if we often run queries based on that field values, we can get better performances, but at the same time, we need to manually take care about data accuracy and consistency. So whenever price of an item changes, total price should be updated as well, and this is called denormalization. Another characteristic of relational model is SQL, or structured query language. It is standard language for managing relational databases. It is used to create queries for retrieving, updating, deleting and entering new data into the database. The language allows users to interact with the database and perform various operations on the data and the database itself. Despite being characteristic of relational models, SQL is so popular due to its ease of use that it is now implemented in many different database models. One of the basic principles of RDBMS and data processing is transaction. A transaction is a basic data processing unit in a database that is executed as a whole. It allows the server to group one or more SQL statements into a logical entity that is executed as a single unit of work. This means that it is executed completely or not at all. The main purpose of transactions is to ensure that a set of commands is executed completely and consistently, and without interruption, and to make the system resistant to errors and unpredictable situations. We will talk more about transactions in further chapters when we start working on practical data. Another key concept in work of transactions that ensures data integrity and consistency during transaction execution is ACID. ACID is acronym for atomicity, consistency, isolation, and durability. So let's further see what those concepts mean. Atomicity means that a transaction is considered as a whole. It is a single operation that will be performed completely or not at all or nothing. This means that all commands within the transaction must be executed as a whole unit, which means either they will be executed completely or none of them will be executed. The role of the transaction is to ensure the integrity of the data and to prevent a situation where only some changes are applied and others are not. To understand atomicity, we must understand how transaction works. If any step or command within the transaction fails, the entire transaction is cancelled, or rollback. The changes made by the transaction until that point are discarded, and the system returns to the initial state before the transaction was executed. If all steps complete successfully, the transaction is confirmed or written, and the changes become permanent in the database. This is called commit. Until then, the changes are located in the server's working memory and transaction log. In short, atomicity refers to the transaction as all or nothing. The transaction must be completed or it must be reversed. For example, in an application that transfers funds from one account to another, the atomicity property ensures that the total value or the sum of the funds in both accounts is the same at the beginning and at the end of the transfer or transaction. So if Bob has 400 euros and transfers a 100 euros to Alice, transaction will make sure that both accounts gets credited, so in the end Bob has 300 euros and Alice 100 euros. This eliminates possibility that transaction gets partially completed or stopped for whatever reason, so only Bob gets credited and in the end has 300 euros and Alice has 0. If from whatever reason transaction fails or is partially completed, it will be rolled back to the state at the beginning. Atomicity takes care of this. Consistency ensures that the transaction will be executed according to the predefined referential integrity rules and relationships, and database constraints. This means that consistency guarantees that the database will go from one healthy state to another healthy state after the transaction is completed, leading to trustworthy and reliable information. If a transaction violates any consistency in the database, it will be automatically rolled back. This means that no transaction may cause an illegal data state. So, let's consider a library database as an example of consistency. Suppose we have two tables, one for books and one for authors. The books table have a book ID as the primary key, which uniquely identifies each book in the database. This ensures no duplicate entries exist for books. For the same purpose, the authors table might have an author ID as the primary key. In the books table, a foreign key column referencing author ID can be created. This ensures a book always has a valid author associated with it, preventing orphan book entries with non-existent authors. For the scenario of maintaining consistency during the updates, imagine updating an author's name from John Smith to J. Smith in the authors table. To maintain consistency, the update process should ideally also update the author's name and all associated book entries within the books table. This prevents inconsistencies where the same author has different names in different book entries, so we can trust that the information retrieved from the database reflects the actual state of the library's book collection and authors. This helps in avoiding errors in reports or queries generated from the database. For instance, searching for books by a specific author will return accurate results without missing entries due to inconsistencies. Basically, atomicity refers to the completeness and indivisibility of a transaction as a single unit, while the consistency ensures that changes made within a transaction do not violate the rules and conditions of the database. Isolation refers to the fact that multiple transactions can simultaneously work with the database data, but they must be separate, and must not mutually influence each other's work. This ensures that the results of one transaction are not seen by others until all transactions are completed or committed. Failure to do so is called read uncommitted or dirty read phenomena, so isolation property ensures they are avoided. It ensures that intermediate results within transactions that are not completed are not visible to other transactions. And the last property in ACID concept is durability. Durability property ensures that once a transaction is successfully committed, the changes it made are permanent and resistant to loss, even in the event of a system reboot, crash or power outage. This is achieved by writing changes to permanently stored media, for example disks, cloud or other media, to ensure that the data remains available even in the event of unexpected system failures. Durability means that the data is secure and permanent after the transaction is confirmed and completed. Once a transaction has started, all SQL queries, commands and changes to the database within that transaction are treated as a single block of operations. This means that all changes to the data within transaction are recorded in the log file. The log file contains information about all changes made during the transaction, including records of rows that are inserted, updated, or deleted, so in case of any issues we can use it to restore the data at any point in time. But we will talk more about transaction log in the next chapter. To sum it up, transactions are critical to maintaining data integrity. They ensure that the database remains in a consistent state despite possible system failures. As we already mentioned, relational model is the most widely used type of database today. Due to its reliability and ability to structure, organize and effectively manage data, the relational model has a wide range of application. It is used in many different industries and applications today. Some of the main areas where they are used include banking and finance. It is used to store financial transactions, customer information, accounts, credits and other financial data. In telecommunications, is used to store user data in telecommunications systems including data about users, tariffs, payments, calls and so on. Business applications. It is used to store and manage business data in a variety of applications, including inventory management, accounting, human resource management and so on. In web-based applications, relational databases are often used in the development of web applications to store user data, content, transactions and other data related to web pages and web services. Also in healthcare, it is used to store medical records, patient information, diagnoses, prescriptions and other relevant medical data. Relational model also play a key role in e-commerce, where they are used to store products, orders, user profiles, purchase history and other data related to online stores. In business intelligence and analytics is used to store data that is used for analysis, report generation and business intelligence to make better business decisions. In education and in management systems of educational institutions, where it stores information about students, teachers, courses and grades. In addition to the mentioned, the relational model and databases often find its application in asset-intensive industries, including oil and gas, chemicals or power production. These industries often employ a combination of relational and NoSQL databases to manage various aspects of their operations. Also, for example in the maritime industry, relational model is utilized alongside NoSQL databases for crew and maintenance management, as well as overall environmental monitoring. In modern marinas, there's a need to efficiently collect and process vast amounts of data related to customers, vessels, installed equipment, maintenance schedules, and available staff. But at the same time, it can include inputs from various IoT devices and sensors, such as those for water penetration, battery voltage, or temperature monitoring for fire protection. By integrating relational and NoSQL databases, such industries can greatly enhance their operations and safety. They can be used for generating timely alerts and notifications to crew members or staff, enabling them to take preventive actions if needed, and thus mitigate potential hazards. Or it can be used as a base ground in systems like enterprise resource planning solutions, where are designed to help businesses manage their financial operations more efficiently and effectively. Relational databases are basically used in all industries and branches of human activity, and play a crucial role in managing data in today's interconnected world. Let's see what are some of the strengths and weaknesses of relational model. Strengths of relational databases are: data structure, a clear and structured data model using tables, rows and columns, which facilitates organization and enables easy data management. ACID principles, high consistency, isolation, durability and atomicity of transactions, which ensures the integrity and reliability of system. SQL, because it enables and allows programmers and analysts to perform complex queries on data, which enables complex analyses and combining data from multiple tables. Stability and reliability, Long-term use and development have resulted in stable and reliable systems. Transactions. Data security and consistency is ensured by ACID transactions. They ensure that database operations are performed reliably, consistently, and with the preservation of data integrity. Also, well-developed mechanisms for competitive access, which allows multiple users to work with data simultaneously. Mature ecosystem. Large number of tools, techniques and experts in case support is needed. Maintenance and security. Relational databases provide tools for security and data access management. Administrators can define user roles and access rights to protect sensitive data. Development support. Relational databases are well-established technology with plenty of tools for development management and maintenance. There are many courses, books, documentation and learning resources available. There is also a large community which makes it easy to connect, learn and solve problems. On the flip side, while the relational model boasts numerous advantages, it's not without its vulnerabilities. Some of the weaknesses are: fixed schema. Relational databases require a predefined schema for data storage. If the data changes, we need to rebuild or to adjust schema again. Challenging scalability. Vertical scaling, where the only option is to upgrade to a stronger hardware, can be challenging and limited. It is also almost always more expensive option than horizontal scaling. Horizontal scaling can be complex for some relational databases because they are not designed for this purpose. Another pitfall is that performance may decrease when retrieving and processing queries with large amounts of data. Although relational databases can be used for applications that use a large amount of data, up to 524,272 terabytes, they are not good in returning the large amounts in a single query. So this can require more careful designing. Less flexibility for unstructured data. Although there are options for unstructured data like file tables and file streams where user can load raw files into the database, the relational database is not designed with unstructured data in mind. Also, the cost of maintaining a large amount of data can be very high with traditional databases. Although not many, these are some of the weaknesses when choosing relational model to keep in mind. And this finishes our Chapter 3, on relational databases. Please proceed to Chapter 4.